NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will factor expressions by adding and subtracting the same term. Then we will use the difference of squares pattern to factor neatly. The key idea is simple. We can add and subtract the same term, which keeps the value unchanged, because plus k minus k equals 0. We choose k cleverly to complete a perfect square. Example 1. Factor a squared plus ab plus b squared by adding and subtracting ab. First, write the expression and then add ab minus ab. Group the first three terms as a perfect square. A squared plus 2ab plus b squared. Then subtract the extra ab. The perfect square becomes left parenthesis a plus b right parenthesis squared, and write ab as square root of ab squared. Now we have a difference of squares. A squared minus b squared. Apply the difference of squares formula. That factors into left parenthesis a plus b minus square root, ab right parenthesis times left parenthesis, a plus b plus square root, ab right parenthesis. Example 2. Factor a to the fourth plus 4b to the fourth. Add and subtract for a squared b squared to complete a square. Group as a perfect square. A squared plus 2b squared squared. Then subtract left parenthesis 2ab right parenthesis squared. Apply the difference of squares pattern to factor completely. Quick challenge. Can you factor x squared plus 6x plus 9 by adding and subtracting a term? Pause the video now and try it yourself. In this lesson, we will factor polynomials by adding and subtracting clever terms, just like grouping. We will use the difference of cubes identity to make a common factor appear. Here is our key tool. The identity a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. We will set it equal to x and b equal to 1 when we see x cubed minus 1. Example 1. Factor x to the fourth plus x squared plus 1 by adding and subtracting terms to create a common factor. Start with the expression. Add and subtract x to not change the value. Group the first two terms together and the last three terms together. Factor out x from the first group to build x cubed minus 1. Now apply the identity x cubed minus 1 equals x minus 1 times x squared plus x plus 1. Factor the common binomial x squared plus x plus 1. Finally simplify the bracket to x squared minus x plus 1. Example 2. Factor x to the fifth plus x plus 1 using the same idea of adding and subtracting x squared. Start with the expression. Add and subtract x squared. Regroup as x squared times x cubed minus 1 plus x squared plus x plus 1. Apply the identity to x cubed minus 1. Now factor out the common binomial x squared plus x plus 1. Finally simplify the bracket to x cubed minus x squared plus 1. Quick challenge. Can you factor x to the sixth plus x cubed plus 1 by this method? Let y equal x cubed, so we get y squared plus y plus 1. The discriminant of y squared plus y plus 1 is 1 minus 4, which is negative 3, so it has no real roots, and it is irreducible over the rationals. Over the integers in x to the sixth, it is irreducible over the rationals. Over the integers in x to the sixth plus x cubed plus 1 is a cyclotomic polynomial, and does not factor into polynomials with integer coefficients. Recap. We factored x to the fourth plus x squared plus 1 as left parenthesis x squared plus 1 right parenthesis times left parenthesis x squared minus x plus 1 right parenthesis. We factored x to the fifth plus x plus 1 as left parenthesis x squared plus 1 right parenthesis times left parenthesis x cubed minus x squared plus 1 right parenthesis. The central trick was to add and subtract a term to produce x cubed minus 1. Then use the difference of cubes identity to extract a common factor. Factor the expression x to the fourth plus 4. We will first add and subtract a convenient middle term to build a perfect square. Strategy tip. Adding and subtracting the same quantity does not change the expression. We'll aim to create a perfect square trinomial. Step 1. Rewrite by adding and subtracting 4x squared. X to the fourth plus 4 equals x to the fourth plus 4 plus the quantity 4x squared minus 4x squared. The added part is 0 in disguise. Group the first 3 terms to make a perfect square. Step 2. Recognize the perfect square trinomial. X to the 4th plus 4x squared plus 4 is exactly the square of x squared plus 2. So we get the quantity x squared plus 2 squared minus the quantity 2x squared. Now, we clearly see a difference of squares. Step 3. Use the difference of squares pattern a squared minus b squared equals a minus b times a plus b. Apply it. Here a is x squared plus 2, and b is 2x. So the factorization is x squared plus 2 minus 2x times x squared plus 2 plus 2x. Reorder each factor for a standard look. That gives x squared minus 2x plus 2 times x squared plus 2x plus 2. Problem 2. Factor a to the 4th plus a squared b squared plus b to the 4th. We'll use the same idea. Add and subtract a helpful middle term to build a perfect square. Step 1. Add and subtract a squared b squared. That creates a perfect square in the first 3 terms. Step 2. Recognize the perfect square trinomial. A to the 4th plus 2 a squared b squared plus b to the 4th is the quantity a squared plus b squared squared. So the expression becomes the quantity a squared plus b squared squared minus the quantity ab squared. Now, this is a difference of squares again. Step 3. Apply the difference of squares 3. Apply the difference of squares pattern one more time. We get a squared plus b squared minus ab times a squared plus b squared plus ab. The factorizations are complete. Nicely done. Here is the problem. Step 1. Rewrite the expression as an alternating sum and difference of triples, so that each triple has the form a squared plus a plus 1 multiplied by a power of a. We write a to the 10 plus a to the 9 plus a to the 8 minus the group a to the 9 plus a to the 8 plus a to the 7 plus the group a to the 7 plus a to the 6 plus a to the 5 minus the group a to the 6 plus a to the 5 plus a to the 4 plus the group a to the 5 plus a to the 4 plus a to the 3 minus the group a to the 3 plus a squared plus a, and finally plus the last group a squared plus a plus 1. Take a quick moment to predict the next move. What common factor appears in every triple? Step 2. Factor a squared plus a plus 1 from each group. Every triple equals a power of a times a squared plus a plus 1. So we have a to the 8 times a squared plus a plus 1 minus a to the 7 times a squared plus a plus 1 plus a to the 5 times a squared plus a plus 1 minus a to the 4 times a squared plus a plus 1 plus a to the 3 times a squared plus a plus 1 minus a times a squared plus a plus 1 plus the last factor a squared plus a plus 1. Notice the same factor repeats throughout. We will highlight them before factoring them out. Step 3. Factor out the common factor a squared plus a plus 1 from the entire expression. This gives parentheses a squared plus a plus 1 parentheses times parentheses a to the 8 minus a to the 7 plus a to the 5 minus a to the 4 plus a to the 3 minus a plus 1 parentheses. That is the fully factored form. As a quick check, treat the chunk x to the 4th plus x squared plus 1 as a single unit. This lets us group the middle terms cleverly. We will add negative 24 and positive 24 to help us factor by grouping. Now, factor out the common unit. Notice that negative 24 times the chunk matches all 3 terms in the group. That gives us a clean quadratic in our chunk a. Let it be the chunk x to the 4th plus x squared plus 1. We now have a squared minus 24, a plus 63. Factor the quadratic in a. We need numbers that multiply to 63 and add to 24. That is 3 and 21, both negative. So the factorization is open parenthesis, a minus 3 close parenthesis times open parenthesis, a minus 21 close parenthesis. Substitute the chunk back in for a, and simplify the constants inside. Problem 2. We will factor the expression. We will complete a square in terms of x squared and y squared, and then use a difference of squares. Add and subtract 2x squared, y squared to build a perfect square. Group the perfect square trinomial and the remaining terms. Recognize the perfect square trinomial. X to the 4th plus 2x squared, y squared plus y to the 4th equals open parenthesis x squared plus y squared close parenthesis squared. Combine the remaining terms to make a clean difference of squares. Now, apply the difference of squares. That gives open parenthesis x squared plus y squared minus 7x, y close parenthesis times open parenthesis x squared plus y squared plus 7x, y close parenthesis. Summary. The first example 1. We want to factor 3x cubed minus 5x plus 2. A neat trick is to add and subtract the same number, which adds 0, but lets us group terms cleverly. We will add negative 3 and plus 3 to create 3 times x cubed minus 1 and minus 5 times x minus 1. Step 2. Now, apply the difference of cubes identity to x cubed minus 1. The identity says u cubed minus v cubed equals u minus v times u squared plus uv plus v squared. Here, u is x and v is 1. Nice. We have factored the expression. Quick check. Expanding the product gives us back 3x cubed minus 5x plus 2, confirming the factorization is correct. Example 2. Now factor a to the fourth plus b to the fourth plus c to the fourth minus 2 a squared b squared minus 2 a squared c squared minus 2 b squared c squared. This symmetric expression factors beautifully by completing a perfect square and then using difference of squares twice. Step 3. Add and subtract the same quantity to complete a square in the middle. We add negative 2 a squared b squared and plus 2 a squared b squared. Then we regroup to reveal a perfect square. Step 4. Recognize this as p squared minus q squared, where p is a squared plus b squared minus c squared, and q is 2ab. We will now use the difference of squares identity. P squared minus q squared equals p minus q times p plus q. Step 5. Factor each bracket one more time as a difference of squares in disguise. Notice that a squared plus b squared minus c squared equals the square of a plus b minus the square of c, and also equals the square of a minus b minus the square of c. This produces 4 linear factors: a plus b plus c, a plus b minus c, a minus b plus c, and a minus b minus c. Example 1. Consider the expression x to the fourth power minus x squared plus 7. Our goal is to rewrite it so a perfect square is visible in terms of x squared. We'll complete the square in x squared by adding and subtracting the same quantity, which is adding 0 cleverly. Watch how we craft the perfect square. The trinomial x to the fourth plus 2 times square root 7 times x squared plus 7 forms the perfect square of x squared plus square root 7, all squared. Now, the expression becomes that square minus the remaining terms. We will combine the extra x squared terms together. This sets up a difference of squares. We can factor it as the quantity a minus b times a plus b, where a is x squared plus square root 7, and b is square root of 2 times square root 7 plus 1 times x. Quick check. If you expand the product, the cross terms will cancel because one factor uses minus b and the other uses plus b. That is the heart of the difference of squares pattern. Example 2. Consider a to the 5n plus a to the n plus 1. We will add and subtract a to the 2n to set up grouping. Now group the first 2 terms and the last 3 terms. Factor the first group by taking out a to the 2n. Then recognize that a to the 3n minus 1 factors as a to the n minus 1 times a to the 2n plus a to the n plus 1. Finally, factor by grouping. A to the 2n plus a to the n plus 1 is common, so we can factor it out. Summary. We completed the square in x squared to reveal a difference of squares, then factored. We also added and subtracted a to the 2n to prepare grouping, and used the difference of powers to finish the factorization. Here are the final answers. Our goal is to cleverly group terms so that a common factor appears. Step 1. Add and subtract a cubed, which is just adding 0 in a useful form. Watch the 2 a cubed terms appear and get highlighted. Now group the first 3 terms and the last 2 terms. This sets us up for factoring. Factor a cubed from the first group. For the second group, use the difference of cubes identity. 1 minus a cubed equals 1 minus a times 1 plus a squared. Replace 1 minus a cubed using that identity. Now, notice the common factor, a squared plus a plus 1 appears in both terms. Factor out the common, a squared plus a plus 1. The expression factors to a squared plus a plus 1 times a cubed minus a plus 1. Therefore, a correct factor is a cubed minus a plus 1. Optional check. If you expand the product, thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.